Let's look at problem 3.19, page 127. How would I do that problem? This is the hard one. I gave you the easy one, 315, which everybody was asking about. I did mention about 315 that you had basically what you were supposed to do in problem 315 is for this reaction time that people were kind of talking about, you wanted to draw two graphs. 108 plus 0.2x 1 was what the prediction equation was by one, at least by one regression formula where an interaction term was not included, and then a different line came out, 101 plus 1.15x1 when the interaction term was included, right? That was for x2 equals to 2. And then you had even a more serious big slope, okay, when x2 was equal to 8. You got a little change in the intercept, all right, for the linear model, for the no interaction term model, so that you got an increase of the intercept. Okay, you got y equals something plus 0.2x1 when x2 is equal to 8, right? You got 116 of 0.2x1, whereas the other term, not only did the intercept change, but the slope changed dramatically to a slope of 8. Okay? So you got a slope of 8 this time. Okay? So that was what you were supposed to do for 315. So to analyze what's going on with the slope, when the interaction term is present. Okay, the slope. Or for fixed x2. Slope in the x1 variable for fixed x2 is changing dramatically when x2 changes. It's not changing at all when x2 changes in the model with no interaction term. That's all you're supposed to observe. Right? Something very simplistic. Okay, let's look at problem 319. Consider the multiple linear regression model with 4 regressors and an intercept. Using the procedure for testing a general linear hypothesis, show how to test the following.
Can I take a stab at it?
Sure.
So we've got a restriction now that B1 equals B2, B2 equals B3, B3 equals B4. And if you look at example 3.7 on page 100, you just have to figure out a matrix that satisfies your constraint you're trying to make.
Okay, you're looking at page 100 for your formula?
Well, just for an example where they do something with a constraint.
Okay.
And so if I set up T such that it's a 3 by 4 matrix,
okay, this is your hypothesis.
right? And so it's going to allow me to get a new S statistic, but I have to find the correct T to give me my restriction that right there.
Okay, there's 2 ways to do this, by the way. There's 2 versions. One is to use the formula 341. Maybe I should show that in the book. This formula using the T. Can you zoom in on that? That's really hard to do.
I'll just reference 341.
Formula 341 on page 101. That's one possible use of application. And there's another method for actually testing the hypothesis shown on the top of page 100. Okay, well, you reduce the model by introducing a reduced model, okay, with the constraints thrown in. I mentioned this because I did a worksheet where I did it 2 different ways as well. Remember that? I calculated SSH by 2 different methods. Okay, thank you for the close-up.
Okay, so the easiest way is actually just to use a reduced model, since we're assuming they're all the same, and you just create a new variable whatever x, that's x1 plus x2 plus x3 plus x4.
That is correct. That is correct.
Okay.
Okay, so the reduced model method is to calculate reduced model method. Okay, 1. Okay, well, I'll just call it method. He didn't give it a name. Okay, but I'm going to call it a name. Reduced model method is to go ahead and plug in all these things into the equation, these constraints into the equation, and you get y equals beta 0 plus beta times x1 plus x2 plus x3 plus x4 plus epsilon. So what you do is you call this a new regressor. Okay? You just call it something else. Call it W1 or something. Okay? And now you have linear regression of y on W. Okay, and that's going to give you a certain residual sum of squares, or error sum of squares, sometimes called also. Residual sum of squares. So you get the SS res of the reduced model. And this model is not going to fit as well as that. Here you have a lot of different parameters to fit with. You can play around, right? And try to connect the dots, so to speak, with your regression equation. But here, you're restricted as to how you can approximate the data. Right? There's a restriction. Right? You only have one regressor now. SS-res reduced model equals, okay, calculate this accordingly. Calculate SS-res for regression, for simple linear regression. You're only going to tell how to do it, so I'm going to be very explicit. For simple linear regression of y on W1, or you just call it W, a W1, okay? That's going to be one calculation. I'll just throw it in into Excel and do it, okay? Versus, and then you calculate SS-res full model equals the residual sum of squares. This is SS-res, the residual sum of squares for the simple linear regression of y and w. SS-res full model, the residual sum of squares for regression, for multiple regression of y on x1 through x4. So multiple regression. Is that clear? Take the residual sum of squares in the analysis of variance table. All right? One for a very simple y and w, where you have to construct w by adding the columns, x1, x2, x3, x4. Just add them. Add the numbers. Is it clear? Not clear? I would have x1 was 1, 2, 3, 4. x2, let's say, was 12, 10, 9, 8. And x3, minus 1, 1, 1, minus 1. And x4 was, okay, make up something else. 3, 1, 5, 9. Okay? Then W was just add this row. Okay? 13 minus 1 is 12, 15. Okay. 12, 13, 14. 12, 1, 5 is 13, 18. 20. Okay? That's my W variable. Okay? So then I have my Y. Alright, Y1, Y2, Y3. So just simple linear regression here. Calculate the ANOVA table, look at the residual sum of squares. That's what this SS-res reduced model is. Simple, right? And the other one is do multiple regression of Y on X1 through X4. Put all those columns, X1 through X4, in the regression tool for X. And then you get the residual sum of squares through the analysis of variance table. Okay, so that's what those are. Then take the difference, and that's SSH. This one is clearly a bigger number, a bigger residual sum of squares, smaller residual sum of squares, so we get SSH is equal to SS-res reduced model minus SS-res full model. Now, how many degrees of freedom in that SSH? How many degrees of freedom are there?
How many things have been removed to be 3 in this case? Or is it...
Okay, well, we could actually just figure out the degrees of freedom for each of the SS-reses. Maybe that's the easiest way. Okay? Notice that this equal sign is not necessary. Okay? So the number of necessary equal signs is the number of degrees of freedom. 1, 2, 3. And you can count it this way. Yeah, I mean, you're going from 4 regressors down to 3. I got to 1. That's the easiest way. 4 minus 1 is 3. Because what's the number of degrees of freedom of SS reduced model? SS-res reduced model degrees of freedom is n minus 2. There are 2 parameters estimated, right? The beta 0 and the beta. And the SS-res full model degrees of freedom were n minus, there were 5. So subtract those, and you get 3 degrees of freedom left over. Okay? For SSH. Okay. N minus the number of parameters estimated. 2 parameters in a simple linear regression model. 5 parameters in this multiple regression model. Okay, including the intercept. Okay. So then you calculate F equals F naught equals SSH divided by 3 divided by the sigma hat MS. I'll put it this way: SS-res full model divided by n minus 5. That's your sigma hat squared. The full, this is your sigma hat squared full model equals SS-res full model divided by n minus 5. Okay, that's what you divide by. All right, and that's your F ratio. Compare F naught with F alpha, comma, how many degrees of freedom? The 3 numerator degrees of freedom and n minus 5 denominator degrees of freedom. You just look at these degrees of freedom. Okay, and if F naught is bigger than that critical or that critical value, then you reject the null hypothesis. Okay, if it's not, then you accept. If F naught is bigger than this, then you reject the null hypothesis. I wrote the null hypothesis up there. At level alpha. Way up in here. Okay, so that's the procedure for 319A. Just read all that out. Do they have any other interesting ones in there? 319? Let's do maybe one more, give an indication of one more. Okay, then they have a... Now, perhaps for this other one, it's easier just to go ahead and use the T method. Let's look at part C. What's the alternative method? 319C. You still have the 5 parameters or the 4 regressors model up there. So this is the model, the full model. Now you want to see if it's possible to reduce it. Okay. With the following. This is just academic, obviously, but let's have a look. See, the other general linear hypothesis you've got here is beta 1 minus 2 beta 2 equals 4 beta 3, and beta 1 plus 2 beta 2 is equal to 0. That's the null hypothesis. You might say, well, where did you get that? But let's not worry about that right now. It's a linear hypothesis. So in other words, there's linear equations in the betas. They don't have to be homogeneous either. You can have, well, as you can see, these are homogeneous. How do I write these as homogeneous equations?
You subtract the 4b3.
That's correct. So I have beta 1 minus 2 beta 2 minus 4 beta 3 plus 0 beta 4 equal to 0. I'm putting in a slot for every beta, okay? And I also have beta 1 plus 2 beta 2 plus 0 beta 3 plus 0 beta 4 equal to 0. Okay? So, and I'm allowed to have any hypothesis like this where I have constant coefficients on the betas and then constants on the right-hand side as well. This is written in the form T beta is equal to C, where T has 2 rows and 4 columns. Of course, excuse me, it should be 5 columns. I should put a 0 here too, because I should have to put the beta as 5 is a 5 by 1 column, because I'm considering the intercept as well. Equals C 2 by 1, where T therefore is equal to the following matrix: 0, 1, minus 2, minus 4, 0. 0, 1, the coefficients of the betas. 0, 1, 2, 0, and 0. That's a 2 by 5 matrix. Beta is, of course, just the beta 0, beta 1, beta 2, beta 3, and beta 4. So I'm checking all my dimensions to get this problem right. And C is the column 0, 0. Okay, because there are 2 homogeneous equations in the betas. All right, and then I can apply the equation 341 that we got the close-up of earlier. We call that the, I don't know, general linear hypothesis method. Okay. And so what you do is you calculate SSH is equal to T beta hat minus C prime T x prime x inverse T prime that inversed, then T beta hat minus C. There should be a prime. Yeah, there was a prime here. It's a mess, isn't it? Okay? Just go ahead. That's for beta hat equals x prime x inverse x prime y. X is equal to the original X matrix for the original model. X 1 1, X 2 1 down to X n 1, and so on. X 1 2, X 2 2 down to X n 2 here, and so on over to X 4, X 1 4, X 2 4 down to X n 4. So the full X matrix. Okay? And beta hat the full model estimation of beta. You could put it full here, right? To make sure that this is the estimate of beta under the full model. Okay? That's SSH. The number of degrees of freedom is the number of rows of T. We're assuming that these rows are linearly independent. And here you see that they are, just by inspection. These are linearly independent rows. So the number of degrees of freedom for SSH is 2. For F naught equals SSH divided by 2 divided by SS res full divided by n minus 5 as before. Sigma hat squared has the same formula. And then you compare with the corresponding F ratio with 2 and n minus 5 degrees of freedom. Excuse me, the corresponding F percentage point of 2 and n minus 5 degrees of freedom. Is it clear how to finish the problem? If F naught is bigger than F sub alpha 2 comma n minus 5, then reject H naught at level alpha. Okay. All right. Let's go to lack of fit analysis. Because it turns out that there's another way to see. Did I give you the notes for today yet?
No.
Okay, let me give you those. There you go. Okay. Gee, need a couple more. Yeah, there. Okay. Did I give you the right stuff there? Looks like I did. There's too many papers. Okay. Note 6, treatment of outliers. We discussed that a little bit. Then the main thing left here is a lack of fit analysis, which you might also ask on the test. I didn't. Let's see. I think one of your problems on Monday has lack of fit, doesn't it? 4, 9, and 418. Do you have anything about lack of fit on that set? Okay. 418? Yes. Yes, there was. 418B has appropriate test for lack of fit. Okay. So we need to really have this for your homework as well. Let's go back to our model assumptions. And so, 418 is not part of your homework?
No, 414.
Okay. Well, make 418 the final exam then. Okay. No lack of fit. So I may ask something about lack of fit on the exam as well. Okay? Here you go, just assign this problem 418. How does that sound? Why not? Okay.
As part of the exam.
Part of the exam. Perhaps. Anyway, we can study this problem, or we can study something I'm going to show you. But it's just a matter of which data you want to use. I'll show you how to do 418, and then maybe I'll give you a different problem. Okay? Lack of fit. Something I want you to do. Be able to do. Got to give you something different to do on the exam. There may be, yeah.
419.
Yeah, 419 is very similar. Okay. So, suppose we have an independent, unbiased estimate of sigma squared available to us besides the usual mean square for the residual. Right? So you have. Well, we're going to show you right now. So I have MS. Res is sigma hat squared. Okay? And so what I'm doing, I'm assuming that I have y equals beta 0 plus beta 1 x1 plus I1 plus and so on plus beta k xik plus epsilon I, right? Where the epsilon i's are independent, normally distributed, variance sigma squared, constant. Right? That's what I'm assuming. I think the model assumptions are given on page 131, the beginning of chapter 4. There's 1 through 5 assumptions. Under those assumptions, the sigma hat squared is an unbiased estimator of the sigma squared. Okay? Basically, this is the normality assumption. Epsilon I NID 0 sigma squared. That kind of summarizes the whole business. Constant variance, independent, normal. So this is unbiased for sigma squared under these assumptions. Let's call this H naught, where there's a specific regression function. Okay, there's a specific linear regression function. Okay? Under H naught. But what if H naught really doesn't hold? In the sense that there's a different regression function. H1, I'm going to have y equals y sub x, I'll put it like this, sub x, regressor values, a vector of regressor values, where x is going to be x1 through xk. Let's put it that way. I'll just write it as a row vector, I don't care. Maybe I'll just not even put the arrow, I'll just put it x. Okay? For vector. Everybody okay with that? Because I don't want that arrow all over the place. I did put it in the notes, but I got tired of it after a while. Okay? Yx equal to phi of x, some function of x1 through xk, plus epsilon. All right, where epsilon I, where the vector epsilon, okay, where again the epsilons are normally an independent distributor with variance sigma squared and mean 0. Okay, you see, if phi of x is not equal to this given form, beta 0, the beta 0 plus beta 1 x1 plus beta k xk, then the epsilon would have a bias. Okay, they'd be still variance sigma squared, but they'd have a bias. Okay, so then ms rest would be biased for sigma squared. Okay. So this is possible. Is there a situation where I don't have to use MS-res for an estimate of sigma squared? Under this general assumption, okay, where phi of x is maybe not equal. Phi of x is not equal to beta 0 plus beta 1 under the alternative. Maybe there's another regressor, okay, where there's a squared term on one of the x's or whatever, okay? No square on the betas, but you could have a square on the x's, all right? You see what I'm saying? This is under H1. Under H0, phi of x is equal to that. All right? So this is the general assumption that I'm making, that there's some regression function, but maybe there's not this one. So I'm still assuming epsilon nid 0 sigma squared the same. Okay? This is still the same. Alright? That's all this thing. Now, that's not real clear in the book, but that's what's going on here. So now, how could I get an independent estimate of sigma squared? Let's look at this. Let's have a little picture. Suppose I did have a curvilinear relationship, but I assumed that it was a simple linear regression model. Okay? Suppose I had something like this. So it actually looked like this. Okay? Not quite as obvious, okay? But how could I get an estimate of sigma squared? I could do it as follows. Suppose I had repeated x values. Okay? So actually what I've got here is I've got a bunch of different y values at this one x value. So assume now that x is repeated, that the vector x, I'll put the vector x, is repeated n sub x times. So that one situation, so I might have like this, I might have x1, x2, x3, and I have 1, minus 1, 1, minus 1, 1, minus 1, then I have minus 1, minus 1, 1, 1. Let's do it like this. Then I have x3 is 1, minus 1, minus 1, 1. Okay? Is any of these triples repeated more than once? No, it's not. But suppose I do it all again. Okay? 1, minus 1, 1, minus 1, minus 1, minus 1, 1, 1. And then 1, minus 1, minus 1, 1. Then what I have is I've got repetitions of this vector and this vector. This is one x value. All right? This is x equals to 1 minus 1, 1. All right? And that's repeated twice. It's repeated twice in each of these cases. So n sub x equals 2 for 4 different x's. And let's see, did I miss one? -1, -1, -1, 1, 1, -1, and -1, 1, 1. Okay. Is it clear what I'm talking about? Just the notation is all I'm asking. All right. He uses a slightly different notation here. So what I've got here is I'm looking at the case of only one regressor, but I've got that regressor value repeated a bunch of times. Remember in that modified Anscombe's data, I had x equals to 5 times, and I had x equals to 8 5 times. Okay, that would have been a case where I had repetitions, sometimes also called repeated measures. I'm measuring the output of the dependent variable numerous times, repeatedly, at a given input. Okay? You have to consider the whole vector as the input. Okay? I'm inputting x equals 1, x2 equals -1, x3 equals to 1, right? That's how you think about it. Right? One input. It's a vector. Okay. So how would I get that? Well, because this model tells me now x is fixed. So what I'm getting is just a sample size n sub x from a normal variable with now a single mean. So if I have y j is normal with mean mu fixed, okay, mu naught, okay, and variance sigma squared, okay, j goes from 1 to n naught, okay, then how would I estimate sigma squared from that? These are independent. How would or even if they weren't normal, I could still estimate it. Okay?
Sum squared over n minus n.
Sum of squared deviations about the sample mean. Okay? Divided by n naught minus 1. J goes from 1 to n naught. Okay? Estimate is unbiased for sigma squared. Okay? That's how I would do it. So I'm going to look at the variability just of these y values in this column, so to speak, column in these 5 data points. In these 5 data points, I need at least 2 to do this. Right? So the minimum number is 2. If I don't have repeated measure, I'm not allowed to do this. But I have a certain amount of variability here. Now, if it's done again, I could get another estimate of sigma squared, independent of the other one. What I could do then is pool the sums of squares and get a pooled estimate of sigma squared. So every time I do it, every time I have repeated measures at a particular input, I can do this operation and get sum of squares. What I'll do is I'll just multiply the n naught minus 1 to the other side. All right, and I'll take the sum of squares, and then I'll pool all the sum of squares together, and I'll divide by the total number of degrees of freedom. Here there's n naught minus 1 degrees of freedom I'm dividing by. Okay, so I'll just pool the sum of squares, adjust it for the mean. All right, pool the variabilities, in other words. Add the degrees of freedom, divide by the total degrees of freedom, after I've added all the variabilities together. And that'll be an estimate of sigma squared. It's independent of whether this is the right regression function or not. Independent of whether this is the right regression function, only assumes that there is a regression function with normal errors with constant variance. Actually, yeah, I don't even need a normality to estimate sigma squared, but later, if I want to make tests of hypotheses, I'll need the normality assumption. F-tests and whatnot. Is everybody following kind of what's going on here? This is called a pure error estimate of sigma squared. All right? This type of a method, because all I'm doing is saying, well, there's error in the model. There's jiggling up and down along some regression curve. All right? And I'm going to estimate that error that way, independent of whether I got my regression equation right. Okay? All right, so that can be done. And then the only other thing left to do is to show that you can therefore partition or decompose SSRes, the sum of error sum of squares, and use this pure error as one of the pieces. So let's just show that with, I think probably the easiest way to, well, I want to mathematically derive that that's okay. Maybe we should do that first. It's a bit of a cumbersome job to do mathematically, but let me show you. It's very simple to do with the numbers. So I have SSRes as this follows. So what I'm going to do is I'm going to do doubly index the y's now according to the input x and the repeated measure index j. Okay? So I'm going to have, my data is going to be now yxj. He calls it yij, but I'd rather use yxj. Okay? All right? For each x, there's a certain number of repeated measures. X goes, in the inputs, okay, and j goes from 1 to nx. Okay. Input vectors of x space. Okay. That's the easy way to describe it, I think. Input vectors of x space. Everybody got the right image? And then I have j goes from 1 to nx. So in that previous example, I had 4 input vectors, and I had nx equals to 2 for each of those 4 input vectors. So it's a double indexing of the y values. Then I have y hat depends only on x, of course. Y hat depends only on x. That's beta 0 hat plus beta 1 hat x1, because that's okay, plus and so on, plus beta k hat xk. For x equals x1 through xk. That's our predicted value. This is the y values, doubly indexed. And then I have SSRes is simply defined to be equal to be summation yxj minus y hat sub x squared. That's a double summation now. As for each x in the inputs, I go from j goes from 1 to n sub x. So what I'm doing here is that for each x value along the horizontal axis, I'm going to sum the squared errors from the straight line fit. Okay? Now, so there's a curve fit here, but there's also a straight line. Okay? From my regression analysis, right? So I'm going to take the sum of squared errors from the straight line, and that's going to be SSRes. You can see how that's going to be wrong, okay, to estimate sigma squared, because this line is in the wrong place. Okay, so now, but now this can be rewritten. Now I'm going to just write the double sum as follows. I'm going to write, instead of yxj minus y hat sub x, what is the natural estimator if you've got repeated measures? What's the right thing? If I could repeat every x, then I could actually just, many times, then I could actually just figure out the exact curve that I wanted to in simple linear regression. If I wanted to use that much data, I would just, well, maybe not exact curve, but I could fit any curve, any polynomial I wanted to, any order depending on how much data I took. Let's say.
I have no idea what you're asking.
Maybe I'm not saying it right. If I want to estimate really where the curved relationship goes, how would I do it?
Use the mean of all the
Mean.
points.
Right. Okay, now you got it. I'm sorry, I was saying it wrong. I get a little bit garbled mouth sometimes. Minus y sub x bar. Okay? Where y sub x bar is simply the average of the y sub xj values. J goes from 1 to n sub x. So it's kind of an ugly looking notation, obviously, here. That's what it is. This difference will give me the actual pure error difference. Then I have to add back on like this, and then square, and over x and j goes from 1 to n sub x. Okay. Now I'm going to expand this square and see what I get. I claim the following. Note, claim, the double sum of the cross product term, x and j. Let's write this y xj minus y bar sub x times y bar sub x minus y hat sub x. I claim this double sum is equal to 0.
Now, why are we adding them together?
I just wrote an identity here.
Oh, okay.
I'm just subtracting and adding this on. Because I want to introduce this difference, because that's going to be the difference I want to study in the pure error estimation. All right?
Got it now.
Okay. So now I claim, if I actually square this out, that the cross product term is 0. So I actually do get a decomposition. Let's see. Well, that's pretty simple, because in fact the inner sum is equal to 0 for each x. Why is that the case? This inner sum is in fact 0 for each x. Here you have a double sum, x on the outside, j on the inside. So this double sum is working for each x. I sum j goes from 1 to n x. Because?
It's j minus y bar.
Yes, this is the deviations about the mean. That's always 0. Sum of deviations about the mean is 0, and this is a constant. Because this is y x bar minus y hat x bar. It's just the two. That's just the two different heights here. So what I'm doing is on this inner sum, I've got this two different heights and differencing them. That's a constant. Then I'm summing on j, and the deviations from the sample mean is 0. Okay? So this is 0 for every j. Excuse me, for each x. Okay, for each input factor. So the cross product term is indeed 0, and so therefore I get what I wanted. So therefore I get obtain SS res is equal to sum y xj, just my y points, minus y bar sub x squared. And here now I'm only going to sum on all x where n sub x is greater than 1. Because otherwise this is just a 0 contribution. Because what is y sub x bar if n sub x is equal to 1? I can also talk about n sub x equaling 1 here. Notice that when I did this doubly index, this made sense for n sub x equal to 1 when there wasn't a repeated measure. J went from 1 to 1. Okay, so this is an ugly looking notation for the y values, but it's okay. And if n sub x is just equal to 1, then y bar sub x is just y sub x at 1, at j equal to 1. And so this becomes 0 in that case. So I'm only going to so what I'm getting is I'm getting this sum of squares plus this sum of squares plus the cross product term, right? So I'm getting so this is equal to this, so therefore this double sum is equal to sum x and j. Y, let me write this step so you won't get lost. Minus y bar sub x squared plus y sub x bar minus y hat sub x squared. Therefore I'm getting the sum of squares like that. So equal to this. So SS res is equal to that. Therefore, SS res can be written as this: nx bigger than 1, because they only get a contribution then, plus sum overall x, n sub x. Now the inner sum is constant in j on the second term. N sub x, y sub x bar minus y sub x hat squared like this. if you're familiar with analysis of variance, you can think of this as the within group sum of squares and the between group sum of squares. And some of you have seen that in statistics, others haven't. We'll see that, in a later chapter, I believe. We might see that again when we do two-way analysis of variance, an application of the regression models to two-way analysis of variance. And let's see, where is that? I think it's somewhere here, probably in chapter 8. Yeah, it's in chapter 8. Two-way analysis of variance. Anyway, this is an analog. However, this is what I'm calling this is my pooled sum of squares. So this is my SSPE, pure error sum of squares. And this is what I call the lack of fit sum of squares, SSLOF. I think we can now go to the worksheet. So what I do is I partition this into two pieces. What's the number of degrees of freedom of SSPE? And what's okay? Well, let's see. I believe it is degrees of freedom of SSPE. It's a little hard to calculate. There's a couple ways you might do it, but basically it's adding up all the nx minus 1s. Okay, what is adding up all the nx minus 1s? Degrees of freedom is summation nx minus 1. Well, let's see. That's the number of sum of all the nx's is the total number of data points, n. Even counting, this is counting the ones. This is the same number, whether I count nx's which are equal to 1, as well as nx bigger than 1, or only the nx's that are bigger than 1. It's the same number because nx minus 1 when nx equals 1 is 0. All right? So let's pretend we counted with all of them. Okay? Whether nx equals to 1 or greater than 1. All right? Then, if I count all of them, then that would be n. And then this would be, and then n minus m, where m is a number of different x inputs. The number of different inputs. Total. Okay? Not having to worry about whether they were repeated or not. Vectors x appearing as inputs. But another way to do it is just to add up to nx minus 1s. In practice, I might just add it up as summation nx minus 1s, that I'm using in my pure error estimations. You're going to see in just a second. So that's the number of degrees of freedom. And then SSLOF would have, let's see, there are n minus p degrees of freedom here. Okay. So then you would just take the difference. So this has SSLOF has m minus p degrees of freedom. He in the book put m minus 2, but he was only applying it to simple linear regression, so it should be m minus p. Okay, let's have a look. It's very simple to figure out the number of degrees of freedom just from an example. So let's have an example. This is the lack of fit analysis for some computer repair service times that I found in another book. So I just...
What was M? You had N, M, and P. Okay,
M equals a number of different inputs, whatever.
Oh, I thought that was P.
P is a number of regressors plus 1, right? Is k plus 1. P is the number of parameters. P for the number of parameters. Okay, you'll see how the M is really only for writing down as a formula is complicated. You'll see in practice how to do it. Let me just do it here. Let's take some data as follows. I have some computer repair time data. There's a number of units repaired on a computer and the number of units of time. as the dependent variable. From, like I said, some other book. Okay? Here's the straight line fit to that data. Hey, it looks pretty good. So there shouldn't be any model inadequacy at all. Now what am I going to do? By way of just saving some time, I'm going to finish this up on the computer. What I'm going to do is notice that there are some repeated x values. Here 4 and 4. Here 6 and 6. Here 9 and 9. And here 10 and 10. Okay? Number of units repaired. It makes sense, right? Okay. That you should have some repeated cases there perhaps. Now, what am I doing for the pure error sum of squares? I need to pool some numbers. I need to pool sum of squares. So now how do I calculate? So for these two y values here, 64 and 74, where am I getting the 50? Let's just go ahead and calculate that by hand. So you can see where I'm getting the 50. Anybody help me with that? What's the average between 64 and 74? That's the y bar sub x. That's 69, is it not? Right. Okay. So, how do I calculate the that little contribution there? So I do y bar sub 4 is equal to 69. Okay. y4 sub 1 is equal to 64. y4 sub 2 is equal to 74. Summation and n sub 4 is equal to 2. There are only two of them. Right? Repeated x values are only two. So I have summation y sub 4 comma j minus y sub 4 bar, okay, squared. The notation is nasty, I agree. But you have to have some. J goes from 1 to 2 is therefore equal to 64 minus 69 squared plus 74 minus 69 squared equals 5 squared plus 5 squared equal to 50. Now, how did I get that with Excel? I said I take the population variance between these two numbers, 64 and 74, and multiply by 2. Why? Because equals a population variance of two numbers, namely 64 and 74. I have a list of two numbers, and then times 2, because the population variance divides by the number of numbers you stick in the formula. So it would be, the population variance would take this plus this squared and divide by 2, okay? Instead of dividing by 1. Because the population variance divides by n, not n minus 1. Okay? So that was a quick and dirty way to get that sum of squared deviations about the sample mean for a sample of size 2. Right? I'm only taking samples of size 2. And unfortunately, in this example, I only take samples of size 2 because all my x values are repeated only twice. Never 3 times or 4 times in any of this data. So I do the same thing here, here, and here. And I add them up, and that's my pure error sum of squares. How many degrees of freedom in that pure error sum of squares? There are 1 degree of freedom for each of these because it's the number of degrees, it's the number of elements in the group minus 1. There are 2 elements, so the number of degrees of freedom is 2 minus 1. If there had been 3 elements in a group, I would have gotten 2 degrees of freedom for that contribution. So I just add the degrees of freedom for all the contributions. So it's 1, 1, 1, and 1. Okay? So 4 degrees of freedom for this pure error. I don't think I wrote that down anywhere. Okay. Then what if, okay, here it's down here. Pure error has, well, I don't know, I did some stuff. Pure error has 4 degrees of freedom. Let's put it this way. 4 degrees of freedom. Let's stick it in there. 4 df. Okay? SSPE has 4 degrees of freedom. Maybe I didn't do that very good job on that. Okay? Now, what's lack of fit is just the other piece that makes up SS res. SS res is 348.8 right here. Right? That's my SS res. This number is less than that. That's good. Okay, it has to be. Okay? The 130.5 has to be. Because indeed, what we had calculated once upon a time on the board over here is that you got two sums of squares equal to SS res. The sum of the two sums of squares is equal to SS res. So you have two positive contributions. Sum equal to 348.8. The other one is called SSLOF, and it's the difference here. You came out to 218.3. SS res has 12 degrees of freedom, so guess how many degrees of freedom SSLOF has? 12 minus 4, which is 8. So in practice, it's just trivial to calculate the number of degrees of freedom of these things. Because you have to do this by hand calculation of SSPE anyway, so add up the degrees of freedom. That's the degrees of freedom of pure error. You don't need some other formula. Okay? Just look at the number of degrees of freedom of SS res, subtract the number of degrees of freedom of pure error from SS res, and that's the degrees of freedom of the lack of fit statistic. What's going to happen is that the pure error sum of squares divided by its degrees of freedom is unbiased for sigma squared, period. Okay? Under the general assumption that we do have some regression function. Okay? With mean zero and constant variance errors, uncorrelated errors. Okay? So under a reasonable assumption of constant variance and uncorrelated errors, okay, then SSPE divided by its degrees of freedom is an unbiased estimated of sigma squared. Here's SSPE divided by its degrees of freedom. That's in the denominator of an F statistic. And the numerator of the F statistic is SSLOF divided by 8. I have to use the SSLOF because SSLOF is independent of SSPE, but SS-res is not independent of SSPE. SSPE is, so you're decomposing SS-res into two independent pieces. One of which can be normalized so that it is unbiased with sigma squared. The SSLOF will be sensitive to departures from the null hypothesis. Departure from the null hypothesis to, let's say, some other kind of curved regression function rather than a straight line. Okay? So then you get a biased estimate of sigma squared in general in the numerator. Okay? That's the theory of the F statistic. And so I get this thing, and I got a 0.837 here, nothing going on. Okay? That's not big. My critical value is 6.04 with 8 numerator and 4 denominator degrees of freedom. And let's say alpha equals 0.05. So I'm just looking at that stuff in the table. You can get this sheet off. I put it in the notes, right? It's in your notes. Okay. Very good. What about if I now extend this? This was an example where actually out of another book where they discussed change point regression, which I had discussed again on Monday, where I discussed problem 3.20, where I looked at the general, somehow set up a model where I had one straight line and then a different straight line, right? Bend the line at a certain juncture, okay? Well, this was the data that was supposed to be consistent with that idea, okay? So now I've expanded the data set. Not only are there 10 components repaired, but there can be up to 20 components repaired now on this computer. And here are the expanded data set. So there's a straight line plot. Okay, it's not the same estimates of the coefficients. What are the estimates of the coefficients now? They are 37 for the intercept and 10 for the slope. 10 minutes per component. Before it was 4 minutes for the intercept and 15 minutes, or a little over 15 minutes for each component. Okay? So now maybe, hey, it takes, longer to set your cup of coffee down because you got a big job to do, but after it goes, okay, you can do more components per unit time. Okay. Now, for the really longer jobs. Okay, well, we'll see. That's an average, of course. It doesn't fit. The model doesn't fit. Here again, I only have repeated values twice for each case, so you don't get to see any three-way repeated values, but I would do the same thing. 3 times various population variance if I had 3 repeated measures. What I've done, I didn't repeat the calculations from before, because in my pure error estimation I already got a pooled sum of squares of 130.5. I don't repeat those calculations, I just continue on. So add all those numbers together, my pure error sum of squares is 215 now. With how many degrees of freedom? This time with 7, I believe, because I had 3 more cases where I had 2 repeated values. And now, therefore, my error sum of squares, or residual sum of squares, has 22 degrees of freedom, right? And my pure error has how many? Did I say 7? So 22 minus 7 is 15 is the lack of fit degrees of freedom. So I take, and my residual or error sum of squares was 7737 now. Big one, okay? Subtract the little old measly old 215, and I get a big lack of fit errors sum of squares. And so now my F statistic, if you do the calculation, comes out to over 16. The critical value is 3.22, so we reject the null hypothesis. So here I'm actually, based with an F statistic, able to show the model is inadequate. That's kind of cute.
So when fitting one of these piecewise models,
yeah,
you just like decide, like, oh, I'm gonna make
the location of the change point is another parameter. Here we just here in this particular example, it was the change point was specified as 10 number of units. So I didn't actually show you the full example.
So if you wanted to create one of those little 2Ds, then you just regress on the first pen and then do a separate thing, and it's not trying to combine the graphs? Or
No. You actually put in the general linear model for the change. Remember I put the column of ones? See, where was that data? Where was that stuff? General linear hypothesis it was under, right? So if I go back to the...
But there's an actual procedure for establishing where that juncture should be.
You have to put it as a parameter in the model. Then it's a nonlinear model, I believe. Where was the general linear hypothesis? Was that it? What did I do here? Is that it? Yeah, that was the stuff. Okay. It was a different problem. It wasn't the computer repair times. I couldn't remember what the computer repair times data was. So then I had taken for x between 0 and 10, it was basically the same idea. I changed it at 10. All right? I had one straight line fit. Okay? So there's no intercept. I think I had modeled this as gamma or alpha 0 plus alpha 1x for x between 0 and 10. And it's a gamma 0 plus a gamma 1x for 11 or 10 less than x less than or equal to 20 or something like that. That was it. How did I write that up? As a linear model. Okay? How did I write that? I wrote it as, okay, I need EY equals, the columns have parameters associated with them, right? So the parameters would be alpha 0, alpha 1, gamma 0, and gamma 1. Everybody clear about that? So this would read y equals x beta plus, or EY equals x beta. So I need 4 columns, and alpha 0, alpha 1, a gamma 0, and a gamma 1 columns for x. Okay? Beta would be the vector alpha 0, alpha 1, gamma 0, gamma 1. All the parameters besides the variance parameter, all the mean parameters. And I need a column. So I need alpha 0 plus alpha 1x as long as x is less than 10. Okay? So here I have my x values, actual x values were 0, 1, 1.5, and so on. And my intercept, so I put 1s here. So I get alpha 0 times 1 plus alpha 1 times 0 for my expected value. And then I'm going to have 0 and 0 here. Okay? Because I don't want any gammas in that part. And then when I get up to x equals to 10, then I switch it. And they go to the second 2 columns. So these are all zeros down here now in my x matrix. Okay? These were zeros up here. And then I go to the 1s here and my data x values over here again. Start them up again at 10. I guess this only went up to 9, and then it started up at 10.5. Okay. Okay. So that's the X matrix. 4 columns, but there's a model without intercept. Now, and then the question came: how do you introduce a parameter to 0 less or equal to x less than or equal to a change point t or something like that? Okay. How do you introduce that? Well, that's a nonlinear model now. You can't do it. So you have to use some other method for estimating t. And then you can also insist on a continuity and so on. There is a spline method, a discussion of splines, where this comes in a little bit. Okay, we're going to talk maybe just briefly about splines. Are we about done? Okay. So now you can do the lack of fit analysis. Okay. So on Monday I give you an exam. Is that going to be enough time for everybody? Okay.
Well, I hope so.
Chapter 4 problems are due. Okay, on Monday. Excellent. Thank you very much.